today I'm going to talk about mapping energy infrastructure with UAV and deep learning. And first, big picture, sustainable development goals illustrated by the United Nations said we need accessible and affordable energy for all. However, by 2020, we still are 600 million people behind the schedule. And to reach this goal, solar home systems have been identified as a promising solution as alternative to grid extension. And to facilitate this process of accelerating solar home system installations, which is basically solar panels, energy infrastructure data about where these solar panels are and how many are they is very crucial for these developmental strategy planning and decision making. However, this data is often not available, expensive, or incomplete in a lot of cases. Therefore, remote sensing plus machine learning is a very promising way of getting those, due to the sunlight absorbing nature of solar panels makes them visible in overhead imagery. So there are a lot of current success using machine learning plus remote sensing to map solar panels, and these are a lot of papers. However, the takeaway is that although these have been done, they are using 0.3 meter resolution satellite or aerial imagery. Well, as the problem solved, then, well, for majority of the population using the off-grid solar home systems, these are actually below 50 watts, which have an area of 0.3 square meters, and actually the satellite would look like this, while the drone can see 5 solar panels, the satellite can see only 1 solar panel. And that single solar panel is actually 100 watts, which is over 50 watts. And therefore, all the home solar systems that people are actually using in off-grid solutions cannot be identified as by the satellite data. So therefore, we have 3 research questions to answer. What is the detection performance, how expensive it is, and how is it applied in real-life scenarios? So we train a convolutional neural network of UNet structure. We pre-train it using some satellite imagery data with solar panels inside, and as you can see, pre-training does help. So the first question we're going to answer is that how is this performance? We're going to define some metrics. We're using precision and recall, and more importantly, the area under the precision recall curve, the average precision, as our metric. We also use F1 score, which is defined here. And the results are listed in this graph. The x-axis is the resolution, y-axis is the performance metrics, up to 4.0 centimeters, and we are actually using our drones to fly, and up with the lower resolution of 4.0, we are actually simulating using the drone imagery we have to simulate satellite imagery effect. And the best available satellite imagery around the globe is 30 centimeter resolution. As you can see, the satellite really cannot find solar panels, while our drones can find solar panels at very high confidence, around 90% recall and nearly 95 to 100% of the average precision. So the takeaway is that drones can be a great source for detecting these systems, and also satellite is not enough. And second, the goal is to measure how expensive it is using drone to collect data. And we have a cost estimation scheme where different buckets of cost estimation are listed. And after we did estimation, the result can be shown in this plot. The upper plot at y-axis is the cost per kilometer squared in US dollars, and the x-axis is the resolution. The lower plot is the same as our previously shown plot, comparing the cost curve and the performance curve. And the colored ones of the upper plot is the satellite price, while the black ones or gradient gray ones are the drone prices. As you can see, with a larger and larger area, the unit price for collecting drone data drops until if we collect large enough, it can be comparable to the satellite cost. However, if we're collecting a small enough area, it is still pretty expensive. And the takeaway number 3 is basically it's still pretty expensive, but however, if you collect large enough, the price can be cheaper than a satellite. Takeaway number 4 is that despite its high cost, it provides an unmatched performance for a high resolution requiring tasks like detecting solar panels. And last, how well does it work in real-life scenarios? Well, we used the public drone datasets from Rwanda, we labeled some solar panels from it, and we applied our method to it. And these are the sample imageries of that village. And overall, we can achieve pretty good results. Maximum recall can be as good as 90% with a precision of 40, and overall, it has a as an average precision of 80%, which is pretty successful. And if we're looking at individual cases, these are the solar panels that were detected. To the left is the predicted, the right one is the ground truth, and the middle one is the RGB imagery. As you can see, they are pretty reliably detecting those solar panels, although sometimes they have like small false positive, but majority of time they detect pretty well. So our takeaway number 5 is that drone imagery can be reliably used to detect solar home systems in complex real-life scenarios, like in Rwanda.